So we're going to talk about intermolecular forces. And as you probably know from English, the prefix inter means in between. So for example, if you have an international agreement, that's not happening within one country, that's happening between two or more countries. And we're going to talk about intermolecular forces, which means the forces that are happening between two molecules. So it's the forces of attraction between two molecules. And if you see the picture there, you've got it in your notes. They're showing the molecules as two little ovals, and they're just showing the attraction between the positive and negative ends of two molecules. Another way to think of it is how much the molecules will grab onto each other or hold onto each other. Again, it's forces of attraction. And these forces of attraction will determine whether something's a solid, liquid, or gas. The closer the molecules hold on to each other, the more likely it is a solid or a liquid at room temperature, because the molecules are close together, as you can see in the picture down here on the left. For a gas, the molecules aren't really holding on to each other very tightly. They're further apart, and that makes them a gas. So the stronger intermolecular forces, or IMFs, will be those of solids, then liquids, and the weaker ones will be those for gases. Now, intermolecular forces determine a bunch of different things, different physical properties. You can see in the video here, if you're pouring honey, you see that honey is usually thicker than water. So intermolecular forces tell you something about the cohesiveness, or the way that the molecules stick together, as well as something called viscosity. And if you've ever heard the viscosity of oil, it's basically how easily a liquid will flow. So if you think about oil or honey or something like that, it doesn't flow as easily as water, and that's because of the intermolecular forces between the molecules. Intermolecular forces will also determine the melting and boiling temperatures. So the stronger the IMFs, in other words, the stronger the attraction between the molecules, the more energy it takes to separate them. So the more energy it takes to melt a solid or to boil or vaporize a liquid. So stronger IMFs correspond to higher melting and boiling temperatures, again, because you're trying to overcome those strong forces of attraction. While weaker IMFs mean you have lower melting points and lower boiling points, because again, there's not as much of that force that you have to overcome. You don't have to put as much energy in to separate those molecules apart. So there's three types of IMFs, intermolecular forces. We'll go from weakest to strongest. There's dispersion forces, dipole forces, and you recognize that arrow, and hydrogen bonding, which is the strongest one, and you've probably remember that from biology, but we'll go over it again. The first one, dispersion forces, are the weakest. They occur in all of the nonpolar bonds. So when you have a nonpolar bond and you've got a pair of electrons being shared equally back and forth, those electrons are moving back and forth, and it's creating tiny little positive and negative charges that will be alternating back and forth. So if you take a look here at the bottom, you see that this shared pair of electrons right now is with the carbon, making the carbon just a teeny little bit negative. The hydrogen's just a little bit positive. Now, once those electrons shift back over, notice how the electrons are closer to the hydrogen becomes partially negative, the carbon becomes partially positive. Again, this is a nonpolar bond, so these are flipping back and forth, and you can see me flipping that back and forth. They're flipping back and forth pretty regularly, creating tiny little positive and negative charges. And that just keeps going. It's almost buzzing. They're moving back and forth so fast. Now, when you have two nonpolar molecules, or two molecules with nonpolar bonds, those tiny little positive and negative charges are constantly buzzing, flipping back and forth, positive, negative, and that will create an attraction between two molecules. Those are the dispersion forces. Right? Because there's always going to be some tiny little positive charges attracting some tiny little negative charges, and vice versa. And they're flipping back and forth. So that explains dispersion forces, those weak forces of attraction. The second one is dipole forces. This is very similar to what we've discussed with polar bonds. Again, unequal sharing of electrons. And what happens here, as you know, electronegativity difference anywhere from 0.5 to 1.7 creates what we call a permanent dipole. In other words, the electrons are flipping back and forth, but they're spending the majority of their time with the more electronegative one. So if you look at the molecule down below, you notice that there is a dipole, a permanent dipole. Oxygen is, as we've been saying in class, hogging the electrons and becoming more negative than the carbon. So this is not a nonpolar bond, this is a polar bond. So what happens when you get two molecules that have polar bonds next to each other? Well, the positive and negative sides of those molecules will attract each other, and this is where the attraction takes place between the positive and negative ends of the molecules. So you have to look at the molecule and see, is it polar? Where are the positive ends, where are the negative ends, and where is that attraction taking place? This is a stronger attraction than just the dispersion forces. Now, before we move on to the third one, it's important to note that a molecule doesn't just have one type of intermolecular forces. A molecule can have one, two, or even all three types of IMFs. If you look at the molecule down below, this molecule has a dipole. We already talked about that. This is a permanent dipole. The oxygen's a little more negative than the carbon. But it also has dispersion forces because it's got those two carbon-hydrogen bonds down here where the electrons are flipping back and forth, creating those tiny little positive and negative charges. So this is an example of a molecule that has both dipole and dispersion forces. Finally, hydrogen bonding, that is the strongest intermolecular force. You hopefully remember some of that from biology. This occurs between molecules that have hydrogens bonded to either a fluorine, oxygen, or nitrogen atom. And we like to say that hydrogen bonding is FON, fluorine, oxygen, nitrogen. Right? So hydrogen bonded to either of those will result in hydrogen bonding. Now, if you take a look here, you see there's a nitrogen bonded to a hydrogen. On that same molecule, you have another nitrogen bonded to a hydrogen. So these will be sites of hydrogen bonding between this molecule and another one. If you look at this one, this is methanol. Same thing here. You've got a site where oxygen is bonded to hydrogen. So this is a site of hydrogen bonding on these molecules. So what's happening here is that the fluorine, oxygen, or nitrogen is so electronegative, hydrogen is basically losing its electron almost completely. So it's like a super dipole, and hydrogen almost becomes completely positive. And the oxygen and the nitrogen and the fluorine become very, very negative. So it's more than a dipole. And you've probably seen pictures like this in biology. What's happening here is you've got three molecules of water, which of course is polar, very polar, and the positive end of the water is attracted to the negative side of the next water molecule. Okay, so it's just all these forces of attraction right here in between the molecules, positive attracting negative. And of course it would go on and on. All right, so this is what you're going to have to be able to do. You need to take a look at the molecules and see what we think about the first molecule in terms of which forces does it have, which intermolecular forces. Well, if you look at this first one, you notice that it has a whole lot of non-polar bonds, right? CH bonds are always non-polar. Obviously, carbon-carbon bonds are non-polar. So it will definitely have a lot of dispersion forces based on all those non-polar bonds. You also see that it has a dipole from the carbon to the oxygen. Right? Oxygen is way more electronegative than carbon. So there's going to be partially negative up here, partially positive there. So that means you're going to have dipole forces as well. This molecule doesn't have hydrogen connected to an oxygen or fluorine or nitrogen, so it does not have hydrogen bonds. If you look at the molecule in the middle, again, you see nonpolar bonds, carbon-carbon, carbon-hydrogen, so that means it has dispersion forces. You also see a dipole between the carbon and this oxygen, double bond, carbon and oxygen, also a dipole, so it definitely has dipole forces. And you notice that there's a hydrogen connected to an oxygen, so there is a site of hydrogen bonding right here. So this particular molecule has all three: dispersion, two dipoles, and a site of hydrogen bonding. If you look at the third molecule, you're getting pretty good at this now. Again, lots of nonpolar bonds, so that means dispersion forces. I see a dipole between the carbon and the oxygen, so that's definitely a dipole. And once again, we have this site of hydrogen bonded to an oxygen, and this will be the site of hydrogen bonding. So we have a similar molecule, not quite the same as the one in the middle, but again, we have all three intermolecular forces. That's not always going to be the case. You could have one, two, or three types of intermolecular forces. All right, so to summarize, this is what you need to know or be able to do. You need to know the three types of intermolecular forces, what causes them, so what's happening with the electrons. You need to know their strength, so which one's is weakest, which one's strongest, and how that would change the physical properties. So for example, if you look at two molecules, which one would have a higher melting point, right, or higher viscosity, or more cohesiveness because of their intermolecular forces. And finally, you need to be able to do what we just did on the previous slide, take a look at a molecule and determine which intermolecular forces are present, right? Is it one, two, or all three? And basically check the box and see if you know which ones are there. All right, now we'll hit some classwork and you can get to practice.